Hey everybody, this is Larry. This is me going Q4 of the weekly contest 317, height of binary tree after subtree removal queries. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. So I think this is definitely a tricky problem, alright? So just to be clear, how many people have solved this now? Okay, actually more people have solved it, but I also just assume that, to be honest, I think this problem is a problem that a lot of the top people have solved, like a similar one, maybe not this specific one, and I wouldn't be surprised if you could Google this. I mean, I don't know, I didn't do it. That said, because I think there probably could be fewer, but it's actually not that bad per se, so maybe I'm wrong. The core part about this problem is noticing and playing around with the property of the height of the binary tree. And what I mean by that is just to figure out what is what matters, right? I guess that's what I'm saying. What matters, or what changes the tree, right? Or what changes the answer if you remove it? I think that's the way that I would think about it. And yeah, I am just setting up my paint stuff. And let me set this up. Yeah, so for example, if you have something like this one, you know, we can do it, you know, by hand, right? In the sense that obviously, okay, we remove this one, or by default the answer is 4, right? And if you remove 7, it becomes 3. I'm using my mouse because I was lazy, but okay, let me take out my drawing pad. Whoops. What am I doing? Yeah, you remove the 7, it takes 3. But we remove 5, it's going to be 3. You move to 4, it's also going to be 3 just because of this way. Also, I think I'm off by 1 here in how I counted. I count the number of nodes, not the number of edges. Doesn't matter, right? Just subtract 1. Actually, that's why I didn't code. So yeah, so now that you figured that out, or that's the way that we do it. And then once you kind of play around with a couple more trees, maybe this one, let me play the other one. Once you play around with a couple more trees, you'll realize that, okay, 4 and 6 is good. 4 and 6 is good. Let's say this one is a potential bad node because this changes the answer from 4 to 3 again. This also changes the answer just because, you know, you cannot go that way anymore to get to the right. And of course the root, but we don't care about the root. And once you play around this, and I don't know that I made it explicit until later of when I was coding this up, is that there can only be one what I call height path or critical path, but I don't think critical path is the right word. But for example, if you have something like this, well, if let's say there are only 2 scenarios, right? Meaning that, okay, starting with the root, the 2 scenarios is, well, 3 if you want to be exhaustive, but by symmetry argument, I'm just going to say 2, meaning that, okay, so there are only 2 cases. One is that, okay, this is a critical path, right? Let's say this is the longest path. That means that removing this node will create a path that requires to go the other way, right? So, and then the other one is that they're both equal. And if they're both equal, then it doesn't matter if you remove left or right, it doesn't change the answer, right? So that's the 2 scenarios. And again, by symmetry, you could do it to the right. So that's basically the ideas that I had. And based on this idea, that's pretty much it. It's just about a lot of bookkeeping, and I'll go over the way that I did it. I don't know that the way that I did it is very clean, to be honest. But you know, an AC is AC, so there definitely is possible that there's a cleaner solution. But yeah. Yeah. Okay, so I actually did it with 3 depth first search. The first one is pretty straightforward. Actually, did I even need parent? I thought I needed to go up to parent, so I actually created this parent thing. So actually, this is not needed. But okay. So first, this is I should name these things. But basically, what this thing does is just to calculate the depth of every node in the tree. It's just kind of a shortcut thing, right? So and the height of, not the depth, but the height, sorry, and what I mean, the difference is that the depth is counting from the root, the height is counting from the leaves, right? So yeah, so actually I'm wrong in here. So okay, so apologies for that. Again, this is my contest code. This is the code that I write when I need to get it very quickly. So my apologies there. But in any case, the height of the tree, starting with this node, is basically what this is saying. And this is just a simple recursion going left or right +1, and then we save it down, almost like a memorization thing, right? And then now so this is the height of the entire tree, and then that's the idea. So the second depth first search that I did is this depth first search. So basically this function is just responsible for saying, is this a critical node? And actually, it's not quite what this function does, but that's what I was trying to keep myself on track on. What it actually does is say, is my left node a critical node, or is my right node a critical node? Either of them, right? And what I mean by this is because, and this is just the way that I thought about it, is that if, actually, I think I was wrong. Now that I think about it, I think I didn't. Well, no. So the way that I did it by looking at the children is so that I could do this count thing, right? Let's say are my children critical nodes, right? And that's basically the idea, is that we get the count, right? We say, is the left node a critical node? If it is, then the depth plus the current. So current is just So the confusing thing is that the current is actually the depth, and this depth is the height. So my fault, like I said, contest code, I wasn't really thinking that much. Yeah, and +1 for the current node. So if this is equal to the height, that means that this is a possible critical path. We also do the same for the right. So if it's right again, then we are at a critical number of count. If count is equal to 0, then we don't have to do anything, because that means that this current node is not on that path of things that would change the answer. So it doesn't change the answer, it doesn't matter, right? If there's 2 of them, that means that you remove either the left or remove the right. It also doesn't matter, because if you remove the left or the right, it doesn't change the answer, right? Because you can think about it as you remove the left, then the right will give you the height anyway, the same height. So it doesn't change the answer. So we can also return early. I think we kind of drew this a little bit earlier on, except for this is more in detail with the 0. Otherwise, then now we do the recursion part, right? Meaning that if count is equal to 1, and that's implicit here, if count is equal to 1, that means that only one of these can be true, just to be clear. But it's linear anyway. So yeah, if this is on the expensive path, then you add that to the bad node. I just like doing it. I don't know. Maybe we didn't need this actually. Or you could do this another way, but I add it for lookup, and then I do recursion on that left, meaning that, okay, we mark it as if we remove left node, this is not good, and then we go recursion. Yeah. Also, it's possible. I think maybe you can do it in both ways, but I added a third recursion just because I think for me it's more straightforward to think about it critically like this. Maybe I'm wrong on that one. I don't know. Because I think you can actually combine these 2 recursion into 1 recursion. But again, we only do 3 recursion, so at worst. So it's going to be linear time, linear space, so I don't really worry about it. Yeah. But otherwise, then now we have a third recursion of this is, I don't know if you can make it out, this is best alternate, meaning that if it's just a thing that I pass in for if, given this node, I took some other path the other way up the parent, this is the answer that I would get. So that means that if I remove this node, the current node, if I remove the current node, best alt is the best answer in the entire tree. So that's basically so that we keep track of it. The entire subtree of the parent, just to be clear. I think that's right. Okay. Do I use it? Yeah, okay. And then now this is just case analysis again, because of symmetry, reasons. Yeah, because of symmetry reasons, both of these are the same. So I'm just going to go over the left one, which is that, okay, if the left node is not none, and it is in a critical path, then we have to do some critical path things, right? So we have to do the math of, okay, if it is, what is the best answer that you can get on the left child if we remove it, if it is bad? So here I go, okay, so there are two ways of thinking about it, right? One is going to the other side with tree. So you have a left node and a right node, and the left node is bad. What is the depth of the right side, right? So that's basically what this part is done. And of course, if you have no right side, then it's just, current plus 1, because that's the size of the thing. And then the alternate is then going to be the path that you took the right side, and also the best alt, meaning that the best answer that isn't in this subtree, right? So that everything outside of the parent and then going the other paths, that's going to be the answer here. So that's basically what best alt is, and I pass in technically the best alt of all these things. So yeah, and then I just do a recursion on this, on the node, and increase the depth. And yeah, that's pretty much it. I know that this is the way, and I think that, these two doesn't have to be different functions, but that's the way that I was thinking about and thinking through it. So like I said, you better have ugly code that works is beautiful, or more beautiful than beautiful code that doesn't work. So yeah, especially during contest time, and every second matters, right? Because I think I finished a little bit like 2 seconds before, after the other person, another person. So yeah. Yeah, and at the very end for each query, if it isn't bad, then we look at the alternate paths. Else we return, or the height of the tree is already given. Yeah, and that's pretty much it. So we do 3 depth first search at most. So this is going to be linear time. We store a bunch of stuff. It's going to be linear space. Yeah, and of course, plus O of Q time and O of Q space. So yeah, so O of N plus Q time, O of N plus Q space. So yeah, that's pretty much it. That's all I have for this one. I'm going to make this smaller so you could see more of the code if you really want. So this is the top, the first 2 recursion, and then this is the last of the recursion. I think you can probably even maybe do it in 1 recursion if you really, no, you need to get the height. At least the way that I thought about it, you need to get the height. Maybe you could be a little bit smarter, but yeah. That's pretty much it. That's pretty much all I have. So let me know what you think. Stay good, stay healthy. Yeah, stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye. Boop, 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 boop. Oh wait, you could watch me solve a live in the contest next, is what I mean to say. So stay tuned for that. I use it again wrong. So let's give it a submit. Okay, cool. That statement that made no sense, but okay. How am I doing? All right, people are already done, so let's get started. Binary tree of n nodes. Each node is contained 1 to n. Okay. M independent. Remove the subtree. So okay. Oh, I see. The height of the tree after performing the if query. Okay, so remove the 4 and there's 2. Okay. Tree rooted at 3. 582. Okay. 581. Okay. 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 How many queries do we have? Let's see. People really got this? Wow. Oh, not yet. All the numbers are unique, so 3, right? So we know that. What is the? So if we do a depth first search, right? What does that mean? How many queries are there again? M is 10,000. People have gotten it though. So there's only one thing. So I feel like This is one of those ad hoc things. Where basically, if you remove it at 6, what is the longest tree? But I mean, this could be very. I mean, we can also do it with what we call it, binary lifting. If we remove 2, for example, it changes. So it has to be on like the only time it changes is if it's on the path. But it could also have a lot of tiebreakers, right? So if we remove 2, so basically it should be a sort of DP. Right, so basically notice none, we return. Basically, how do I process this? Because then now you're trying to think, well, because you're trying to go up the tree, but the going up the tree may time out. This seems like a scene problem, but because now you removed it, it's on a critical pathway, so let's do that okay. So let's find the height of the tree first. Okay, fine. Right. Right. So then here we have the height of the tree. Right. And now we know that yeah, so then now we can calculate all possible critical paths, right? So if right, oh jeez, so that means that this. Do I really need binary lifting? Is that really the only thing? So basically, if this answer only changes if we remove 2. 285. How do we do it? 2. Okay, so also maybe I should just do a counter thing. It'd be much easier to do it again. Okay, and now we go, okay. Oh, I just finished it. Basically, does removing this node change the answer is what we want to do, right? And on top we can go, okay, well, like if we remove this node, does it change anything, right? Now what we want is actually yeah, dep basically if okay, so if count is 0, we can just return. Doesn't mean anything. If count is equal to 2, what does this mean? That doesn't mean anything about returning this node, but it means that removing the child doesn't change the answer, right? So then we can also return because we just don't process. Otherwise, if count is equal to 1, then we do it again maybe. If this is the case, then bad is, this is actually dot left dot value. And then go to of no dot left current plus 1. I guess this is implied, so we can take this off. Okay, and then now just for kind of just kind of print bad, I guess, just to see. So if I'm right, then the critical path should be 7, 5. No, not 5, but 7. I guess only 7 and 1. I don't know if we can return to root. Oh yeah, it's not going to return to root. But so 7, 4, 5 is wrong. And 8.2 is wrong too. Well, 8.2 is right actually. Well, 8 is right. Oh yeah, 8 and 2 is right, but not 4, 5, 7. Why? Because we move 5 because it thinks it's, we move 5, then it doesn't. But then okay, because everything is in a, so it thinks that the critical path from 1 is going to be on the right, which is true. It removes, oh no, yeah, it removes 5, it changes the answer. It removes 4. Okay, actually the code is more right than I am. So okay, so then now how do I get the answer now that we know these are bad nodes? Okay, so then now maybe we do something like okay, how do I do it? So okay, how do I do the, I think now we're okay maybe, but I don't know how to do the bad notes. Or how to get the answer taking away the bad notes. So getting rid of 7, and getting rid of the 5 and getting rid of 4, right? Okay, so then we can look at the parent and then look at the longest path of the parent, because then the parent can contain, say, with the alternate. Okay, fine. Maybe. Otherwise, then okay. So yeah, and then we also want to do something like okay, and then now we do of okay. I don't know how to do it quite well. So we can get rid of the entire thing, but how do we get rid of just like say the 7 up there, right? I guess we do a depth for search, so getting rid of the 7. If no dot right is bad, then is it binary lifting? I don't want to do binary lifting. That's why. So we got the critical nodes. So 10 to the 4. No, that's gonna be too slow. We don't do anything optimized. Okay. Going out to 5. Okay, so then now we pass the maximum thing right on the other side. Okay, fine, I see. Maybe, I don't know. We'll see if this is right. Okay. It's by definition, multiple nodes on a thing cannot be it. So okay, so if node.left is in bad, dot value is in bad, okay. if this is bad, then if this isn't bad, if neither of them matters, then we just don't care about processing anymore, right? Is that true? I think there's just one critical path that's a line in between. So okay, so left node isn't bad, then we do depth of node.right.value, alternate is equal to this, and then right, okay, so if this left is bad, then it's either the best alternate, so the depth of the other one plus current plus 1, this is the depth going the other way, and also best alternate. So then alt dot node dot left dot value is equal to this, and then we curse on the left with the no, is it? Yeah, and then current plus 1. Okay, and then now we print out afterwards, maybe. I have to make sure that this is not none, of course. Okay, so I mean, I have to check if tab. Oops. Nope, it's current plus 1. Okay. The answer is 1, but I think I'm off by 1, but that's okay. Maybe. Okay, so then now for query. If Q isn't bad, then just H for height. Okay, so this is the right answer, -1, whoops. Because I counted one more node or something like that. Okay, let's give it a submit. Not quite confident about this one, so we'll see if there's edge cases. Yes. Okay. I mean, that was... Yeah, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's contest and all these problems and this problem that I just did. Stay good, stay healthy, take good mental health. I'll see you later and take care. Bye-bye.